In this lesson, we're going to continue talking about slope, or rate of change. This time we're going to be talking about graphs. Last lesson we looked at rate of change or slope in terms of tables. We're going to review that in this lesson, and we're going to look more at graphs. So let's start with just a definition of what slope is in terms of graph. Really, it's just the change in the vertical distance over the change in the horizontal distance on a graph. Now, that's a lot of words to squeeze into this little space here, but I'm going to give it my best shot here. So, slope is the change in vertical distance over change in horizontal distance. So I don't think I'm going to make it, but let's give it a try. Over change in horizontal distance. I'm going to have to go above the line here. Okay, that ain't pretty, but that's what it is. Slope is the change in vertical distance over the change in horizontal distance. Let me just draw a little picture for you. We did look at some graphs yesterday. Sorry, still a habit of me to say yesterday. Last lesson. So if we have this graph, and let's say I was to just picture a graph here. This is the graph. The other part was just the axis. So here's my graph. It's linear. Remember, slope is the steepness. For a linear relation, it's the same steepness everywhere, right? No matter what part of the graph I look at, it's going to be the same steepness everywhere. So let's zoom in a bit if I can. All right. So in other words, remember, it's the change, I just defined it as the change in the vertical distance over the change in the horizontal distance. So let's say I started at this point here, and I wanted to go to this point up here. All right, so I'm just drawing these dotted lines to break down the vertical and horizontal distance. So this here is the change in the horizontal distance, right? Remember, on the horizontal axis, that's x. On the vertical axis, that's y. So really, that change in horizontal distance is just delta x. That's something we talked about yesterday. So just wrap your head around that. Change in horizontal distance is delta x. Change in vertical distance is delta y. It doesn't matter where on the line, what 2 points I choose to measure the change in horizontal distance and vertical distance, because they're going to change proportionally. So I could have taken that spot, I could have taken a couple points farther apart, I could take a couple points closer together just to illustrate. Let's say I picked these 2 points, which are much closer together. It doesn't matter, because you can see that my horizontal distance is much less between these 2 points, but my vertical distance is also much less, and they're proportionately changing. So wherever I measure between any 2 points on a line, the slope will always be the same. Both delta y and delta x will change proportionally, and I can get the slope from that. Remember, it's just delta y. It's the delta y over delta x to get rate of change. And remember, rate of change is another term for slope. So slope is just another way of talking about rate of change. How much is one variable changing compared to another? But when we're talking about graphs, we definitely talk about slope quite most of the time. So here's some examples: steepness of a line, pitch of a roof, the grade of a road. Those are all things that we can talk about, the steepness of, the slope of them. When we're talking about slope in this course, we're going to use the variable m to represent it. All right? So the reason that we use the variable m is it actually comes from the French word monter, which means to go up or to ascend. So, M for monter, the first letter of monter. So, whenever we talk about slope in an equation, we'll use the variable m to represent it. So, slope is the ratio of the vertical distance to the horizontal distance. The formula that we use can be written in several forms. Well, we've already seen these forms here, delta y over delta x, which is the same as, first difference over change in x values. That's just rate of change. So those ones I just highlighted, we saw in our last lesson. But maybe I won't use the green highlighter there. But what's sort of new, but it's the same thing, is m means the same thing. M stands for slope. Again, that's just a short form, so you don't have to write the word slope out every time. M is equal to the vertical distance over the horizontal distance. I'm kind of working backwards here as I read through this equation. But so vertical distance over horizontal distance, we just saw that. I just showed you that on the graph. Vertical distance is delta y, horizontal distance is delta x. And in just common terms, we call that the rise over the run. All right? So rather than having to say vertical distance divided by horizontal distance over and over, we say rise over run. That should bring to mind, when you see it, what we're talking about. So delta y on a graph is just the rise, because it's up and down. Delta x is the run, as in it runs from side to side. Rise over run. Rise is wise. Rise is on the y-axis. That's one way I tell people to maybe, hopefully remember it, because rise rhymes with wise. So there's the formula. These are all the exact same formula. That's what the equal sign between them is showing. Slope is the same as rise over run, which is the same as vertical distance over horizontal distance, which is the same as change in y over change in x, which is the same as first differences over change in x values, which is the same as rate of change. All right, find the slope of the following relation. Well, this is going back to what we did last lesson. So we need to check our delta x, our change in x's. 2 to 4 goes up by 2. 4 to 6 goes up by 2. 6 to 8 goes up by 2. First differences, or delta y, right? That's another way that we identify it. Goes from 6 to 3, down by 3. That negative sign is crucial. You have to be paying attention to whether you're going up or down from one number to the next one. Because if you leave out the negative sign, you're saying something very different than if you put it in. So in each case, as we go from one number to the next down the column, we're going down by 3, so it's negative 3. So the slope, m for slope, is equal to, I got all different choices, right? But whichever one I look at, it's going to be the negative 3 goes on the top, because that's my delta y, or my first differences, and it's going to be 2 on the bottom, because that is my change in x values, or delta x. And again, remember, I could change that to a decimal. I could change that to negative 1.5. But I like to leave it as a fraction. So now we've got a negative slope. This is the first time I think we've really looked at a negative slope. So let's just do a quick sketch to help us visualize what that means. So if, let's say, 2, 4, 6, 8 here. Two, 4, 6. Okay, so we've got an ordered pair at 2, 6. We've got another one at 4, 3. We've got another one at 6, 0. We've got another one at 8, negative 3, so I'll just ballpark that as being down here. The graph looks like this. Now this was just sort of a rough graph, so one of my points didn't quite hit it. Let's see if I can move that one over. Fudge it a bit, in other words. There. All right, so there's all my points on the line. What do you notice about this line? Well, hopefully you're noticing that it's going downward from left to right. All the examples I've done up till now, including this one, as I read the graph from left to right, it's going up. This one is going down as I go from left to right. That is why I'm making such a big deal about the negative signs. The fact that my slope is negative 3 over 2 reflects the fact that this line goes down. So, we need to pay attention to negative signs. A positive slope, a positive m, will always go up to the right, like this. That's a positive slope. I never calculated it because it was just an example, but that would be a positive slope, whereas this is a negative slope that goes down from left to right. Pay attention to the signs. Find the slope for the following relation. Okay, sure. Before we do that, just take a look at it. Is this going to be positive or negative? Well, it goes up as we go from left to right. So we expect this slope to be positive. Now remember, in the example that I did at the top of this lesson, I showed that it doesn't matter where we calculate, as long as calculate our slope, as long as we get 2 points, because the x and the y, the delta x and delta y, are going to change proportionally. So I can pick any 2 points. So let's say, just for argument's sake, that I pick this one here and this one all the way over here. So I pick a big spread between them. All right? So just draw a dotted line along here to show how far from left to right it's going and how far up or down. Remember, this is my rise. Sorry, that's not my rise, that's my run. This is my run. It's going from left to right, side to side. So if I go from negative 4 on the x-axis all the way over to 6 on the x-axis, it's going up by 10 units. The rise, if I go from negative 1 on the y-axis up to positive 4, it's going up by 5 units. So from this, I can see that m, slope, equals rise over run. Didn't write the word rise in there. There we go. Rise over run, which is 5 over 10, which I should always reduce to 1/2. And there's no units in this one. But that's my slope. It's positive a half, right? I predicted it was going to be positive. It is positive, and the actual units, or the actual number, is 1/2. But I didn't have to pick those 2 points. That's what I'm trying to get at. I can pick any 2 points. Let's just pick a couple other points. Let's pick a couple that are closer together. Say that green one and this green one here. Well, now I'm just going from here to here. Now my rise, I'm going from 0 on the x-axis over to 2. And I'm going from 1 up to 2 on my rise. Rise, run. So, slope equals rise over run, which equals 1/2. These are the exact same. So it doesn't matter where we take our points, as long as we do follow the correct rise over the run and do it carefully and correctly, we're going to get the same slope. And we also have to reduce them, right? If I hadn't reduced the first one I did, I might not have noticed that they were both 1/2. If I just left it as 5/10, then maybe I might not have noticed. All right, next example, total cost versus number of classes. So imagine you've signed up for classes for something. So my independent variable is the number of classes. Cost is on my vertical axis is my dependent variable. Maybe it's at a gym, maybe it's for something else. But you can see there's a relationship given by this graph. So if I want to find out the slope of this line, again, I can pick any 2 points. I want to pick points that are as easy as possible for me. So maybe I would start with this one right here at the, right here at the y-axis. That's always a good one if I can read it. And then I find another point somewhere where it clearly goes through some grid lines. So here is a point that I can clearly see is right in the middle of some grid lines. And again, we're going over by from, well, I have to read off the scale. So my run goes from 0 to 4. So it's going a run of 4. The rise, remember I have to read the scale here. So I'm actually starting at 60 on the rise, and I'm going up to 120. So that's something else to keep in mind. So from 60 up to 120, it's going up by 60. And so the slope is equal to rise over run, which equals 60 over 4, which equals 15. I can reduce that. 60 divided by 4 goes in evenly, so it's 15. And there's units involved in this one, the total cost. So the rise was in dollars, so it's $15 per class. Classes was the units for this. So the slope, the rate of change, tells us something. From looking at this graph, I can see that it costs $15 per class for whatever this is that I'm signed up for. Last one, here's a relation of rain in a barrel versus time. So someone's pulled a plug out of a rain barrel to let the water come out, water their garden. We can see certain things like the rain barrel starts at 100. So in other words, there's 100 liters of water at time 0, and then it goes down. Now I would say that it's going down at a constant rate. There's no line connecting it, but we certainly could, because volume and time are both continuous variables, and so we certainly could connect this with a line if we chose to, and I think I will, since we can. All right, that way I could even see, if I wanted to, I could predict about how long it would take for the for the barrel to completely empty. Now my line isn't perfect, it's off by a little bit, but at least it gives me an idea that, okay, it's going to be around 7 minutes for this rain barrel to empty, although I didn't quite get it perfectly lined up. Anyway, if I take my 2 points, again, I've already got that one at 0, 100. Maybe I'd pick another one over at 440. I like to have them far enough apart so that when I draw my little lines like this, I got a little room to write stuff. My run, in this case, is going from 0 over to 4. And the rise is starting at 100 and ending at 40. So it's starting at 100 and it's going down to 40. If you've been paying attention to what I've been saying up till now, that means it's negative. We've gone down by 60 liters. That negative is important because that'll give us a negative slope, which you should have already predicted from looking at this graph, which is going down from left to right. So, slope, rise over run. So, negative 60 over 4. Which gives negative 15. And again, there are units, but this time it's not dollars and classes, it's liters per minute. So, how do I interpret that? That means the water's flowing out of this barrel at a rate of 15 liters per minute. So, as you can see, we can get some really good information about a relationship from looking at the rate of change or the slope. So that's definitely something that we're going to be coming back to again and again and again over the next little while. So you really should aim to get a good handle on how this works. And you can do that by working on the homework that goes along with this lesson, which you will find in OneNote.